Good morning. We have started discussing about matrix approach for structural analysis, and in the last lecture we looked at the basic concept behind the flexibility approach for a statically determinate truss. Today we are going to continue that. Please understand that in the last lecture, the problem that I looked at, I was just looking at it. I didn't solve the entire thing purely because I was just explaining the concept. Later on, we will have enough opportunities to look at problems. Right now, the way I look at all my lectures, I first look at all the concepts, use problems only as illustrative purposes to explain the concepts, and then once the concepts are described, I move on to solving problems in their entirety, so that you know how to use the method in applying it to problems. Okay, so today we are going to be looking at the flexibility method for beams and frames. The essential difference between what we did for truss last time and what we are doing for beams and frames is that they are flexural members as opposed to axial members. In other words, flexural deformations. Okay. Now, just like we saw that in a truss, you started off by looking at the truss structure and then looking at the member forces in terms of the external loads, and from there we moved on to solving the structural problem. Okay. So now let us look at a member. A member which has flexural deformations. Now, what are the member end deformations? We've already done this. I don't want to go into this. It is going to be theta 1 and this is going to be theta 2. Okay, and corresponding to these thetas are essentially due to moments M1 and moments M2. Okay. Now, in addition to this, there may be thetas due to loads on the member. Okay. So, if we write down this, we will see that we've already written this down. I am just explicitly writing it down. Theta 1 is equal to L upon 3EI. I am actually going back to the old and just rewriting it in this form, and then plus theta 1 0. What is the theta 1 0 due to? Understand that theta 1, the rotation here, would be related to M1, M2, as well as theta 1 0 is the rotation at the left end due to the member loads. So, this aspect is due to member loads. So, similarly, theta 2 is equal to minus both of these are due to member loads. Okay. If there are no member loads, then these two are 0. Okay. So, this we have already seen. So, now I am going to rewrite in this format. Okay. So this is the format that I'm going to write it down in. Now let us see what these terms are. These terms, if you look at them, Vi is equal to theta 1 and theta 2. So in other words, the member deformations are the rotations at the two ends. Okay, this is the member deformations. I am using the same notation that we are going to be consistently using in this approach. Okay, then what is SI? SI is equal to M1, M2. What are Vi0? Theta 1, 0, theta d 0. Vi0 is due to, and I will call it in a broader sense due to member effects, because we've already seen that it's not, rotations can happen not just because of member loads, they can also happen due to temperature, etc., etc. We've already discussed that, so I'm not going to go into the details. Finally, what is Fi? Fi, if you look at it, is L upon 3ei minus L upon 6ei minus L upon 6ei L upon 3ei. So in other words, if these are defined in this fashion, then this is valid, because this we know is valid from earlier. Okay, so this is what we are going to be going with. This is one relationship. The other relationship is what is this relationship? If you look at this again, all it says is how we get the member end moments corresponding to the loads apply at joints. Remember that loads apply on members are already considered in the effect that we considered in Vi0. Okay, so this is just member end loads. So if you really substitute it in here, we will see that ultimately we get displacements, okay, in exactly the same way. I'm not going to go into the details, but once everything is set up, you will see that this is equal to the same terms, the way I wrote them. Exactly this thing is valid, because once you use this, plug this SI, substitute the value of SI into VI, all those things, and you will see here that this is one thing, and then there is plus, this is one additional term, I Vi transpose Vi0. This is a very important term. These are member end rotations due to the loads applied on the members themselves, and therefore by using virtual displacement, you will see that R can be related in this form. Okay, so this in a sense is the final form of R is equal to summation here this is for a flexural member, it's 2 by 2. For flexure, it's 1 by 1 for axial. Okay. Now, if this is n by 1, then by definition this is going to be 2 by n or 1 by n, depending on whether a flexural member you are finding out the member and moments, or in an axial member you are trying to find out the axial force in terms of this. This correspondingly is going to be either n by 2 or n by 1. This is going to be equal to a 2 by 1 or a 1 by 1. Now, I have this question. I did not introduce this in the truss, but I am introducing this here. What is this effect for a flexural member? We know what this is. This is due to member effects, for example, member loads, temperature, etc., etc. In a truss, where would this come from? This would again come from member effects. And what are member effects that we have already considered? These member effects may be temperature, or elongation or contraction due to temperature change, or lack of fit. Remember that. Okay. So this is member effect, and this one again is either n by 2 or an n by 1, and ultimately this is an n by 1. Okay. So this in essence defines the flexibility approach for structural analysis. How do we find out the member forces? Member forces in terms of the external loads are this. So these are the member forces. Remember that all of this is for a statically determinate structure. Okay. So this in essence defines, these are the member forces related to the structure loads, and these are the structure displacements corresponding to the loads. Okay. So that in a sense is the definition of your structural analysis. Find out the member forces and find out the deflections. Now this again is for a statically determinate structure. Now let us see, for once we have this, how we can apply it to a member. Okay. And for a beam, okay, it doesn't make sense. So I'm going to take a frame. So let us take a frame problem, okay, and see how we deal with this. Of course, the frame has to be statically determinate. Again, I am not going to go through the entire problem. I am just going to list out how to get what we want to. Okay. So now, if you look at it, okay, let us put some loads on this structure. Okay. So let me say that let me put some numbers here. So this is EI, this is EI, this is EI. Okay. Let us say that this is 5 meters, this is 5 meters, so is this 5 meters. All of them are 5 meters. Okay. This load is let's say 40 kilonewton. Okay, and here what we want to find out is, I want to find out the, I mean there are lots of things to find out, but let me just tell you, I want to find out the member end moments, because once I know the member end moments, I can draw the bending moment diagram. Okay, so I want to find out the member end moments, and let's say that in this particular case I want to find out how much well, let's put some other number. Let me put something else. Okay, let me put 10 kilonewton here, and I want to find out what is the displacement of this joint. In other words, the lateral, note that since all members are actually rigid, automatically the displacement, horizontal displacement of this will also give me the horizontal displacement of this. Okay. In addition to that, let me find out how much this goes by. Okay. So these are my two questions. How much does the top displace by, and how much does this? This is my overall statement, and I also want, so therefore the question is find member end moments. Once we find out member end moments, you can actually draw the bending moment diagram. Okay, and what else? R1 and R2, the values of R1 and R2. So this is my problem statement. Now I have to understand how I am going to go about this. And look at this, and you will see that this is essentially a statically determinate structure. So let us see how we are going to go about it. Now the first step in this problem, what do we find out? For each member, we find out its member end displacement, and so I have here, let me qualify this. I'll call this member 1, this member 2, and this member C. A, B, C, D. So AB is member 1, BC is member 2, and CD is member 3. Okay. So now the first step for each one to write down the member force deformation relationship. So for AB, okay, for AB, what is the this thing? There is no load, okay, and therefore VI, which are the two rotations at the two ends, are equal to, I'm going to write this in this format, L upon 6 EI, and L in this particular case is 5, and note. See, 2L into upon 6EI is L upon 3I, which is what you have, multiplied by SI, which are MAB and MBA. Since there is no member load, so for AB, which is member 1, for V1, this is it. Now, for member 2, this has a load of 40 kilonewton acting here. So the first thing that we have to do, understand that V2, the first part is this, but there is an additional Vi0, V20 that we have to write down. And that V20, how do we find out? Well, we find out under this, it's going to reflect like this, and we need to find out this and this. How do we find that out? Under this, I think we have done it enough, so I'm just going to write it down how to find it out. This is going to be this is M, this is M1 and M2, this is M2, and once we go through the entire process, we see that theta 1, 0 is going to be equal to, in this case, 50 into 5 by 4. By the way, minus because these are opposite to each other. So 50 into 5 by 4 is this part. For that, it's going to be equal to 2 by 3. And then you'll have minus 50 into 5 by 4 into 1 by 3. And so essentially theta 10 is equal to minus 62.5 by EI. Okay, and theta 20 is equal to 62.5 EI. Okay, that is actually, if you look at it, it'll work out to P L squared upon 48 EI. Okay, but doesn't matter. We've computed this. Okay, so for V2 is going to be equal to 5 upon 6 EI. 2 minus 1 minus 1, 2. MBC MCB plus 62.5 upon EI minus 1 plus 1. And V3, since there is no load on it, is going to be equal to V3 is going to be equal to 5 upon 6 EI, 2 minus 1, 2, MCD MDC. Okay. So these are, we have written down the force or deformation force relationship for each member. Okay, this part is the F into SI, and this part is the VI0. For V1 and for 1 and 3 there is no VI0. For 2 there is a VI0 which we have computed. Okay. So now the question comes, next what? Next is evaluating SI R. Okay. This is very, very important. Okay. So how do we find out this Si into Bi R? What is R? In this particular case, R is, since we have, what are we finding out? We are finding out small r is equal to R1 and R2. Those are the displacement at the top and at the hinge. Okay. If you look at this, therefore capital R, sorry, this is this way, capital R will be R1 and R2 corresponding to the forces. Okay. So if you look at this particular concept, that means in this particular case, what is R equal to? It is irrelevant what we are getting. R, you will see, will be equal to 10 and 0. In this particular case. So how do we find out Bi? What we do actually is this. We found out, so this is 2 by 1 and this is 2 by 1, this by force has to be 2 by 2. Now this 2 by 2 has two columns. For each column, the way we find out the column vector is this. Put R1 equal to 1 and find out the member and moments. Put R2 equal to 1 and find out the member and moments. Okay. So if we look at that, this becomes so this is 1. Then how would we do? If you look at this, you will see that this gives rise to 1. So the reactions sigma fx equal to 0, sigma m equal to 0 take moments about this point, and then sigma fy equal to 0 gives me all of these. And once I have all of these, okay, my member and moments become this. So how I find out the first column of B1. I am finding out the first column. So I am finding out the first column for B1. What would that be? Let's look at it. A. So I am finding out. So if I look at this, I can draw the bending moment diagram. How would the bending moment diagram look? It would look like this. This would be 5. Here, this would be going in this fashion. And over on BC, it's going to be like this, 5 and 0 here. And this is going to be and over here it has to be 0 because this one doesn't take any moment. Okay. So if we look at it, B1, okay, at this MAB, what is the moment? 0. So this is 0. At this point, what is the moment? Anticlockwise 5. So anticlockwise 5 is plus 5. Let's find out B2 0. It's clockwise, at this end it's clockwise 5, so this is minus 5. Here it's 0, so it's going to be 0. What about B3? B3 you will see is equal to 0, 0 because there is no moment at this end. So this is the first part for R1 equal to 1. Then we are going to put R2 equal to 1. So let us put so I am now putting R2 equal to 1. If you look at this, this will give rise to this, and these two are going to be equal to 0. So how will the five okay 5 5 5. This is the bending moment diagram, and therefore if you look at B1 due to R2 equal to 1, this is going to be equal to 0, and this is again anti-clockwise, so it's going to be plus 5. B2 is going to be, this is clockwise, so it's minus 5. Here it is anti-clockwise, so it's plus 5. B3, here it is clockwise, so it's minus 5. Here it is 0. So ultimately, having done these, if we write down B1, this is going to be equal to 0 plus 5 plus 5. That is, this is coming from R1 equal to 1, and this next one is coming from R2 equal to 1. Similarly, R1 equal to 1, R2 equal to 1. Each column B3, R1 equal to 1 and R2 equal to 0. Now here, what are the, for B1, what are the things? This one is SI is written in this way, MBC, MCB, and this is equal to MCD, MDC. Okay, this is S1, this is S2, and this is S3. So now, if I have got these, now I can plug in. What is my R? I know I have already given my R. R is equal to plus 10, 0. Okay, so I can find out my SI very easily. So that's the first step. Find out the member end moments. And if you look at the member end moments, you will see that they are equal to okay. If you put in, you will get S1 equal to 0 plus 50, S2 is equal to minus 50 and 0. S3 is equal to 0, 0. Satisfy yourself that this is indeed the case for this particular problem. Okay. Now, we will see, we will come to problems later where we will see that this is not a complete picture of my SI. Okay. In fact, SI actually has some additional terms that we will look at later. I mean, right now I am not too concerned with this. For this particular problem, you will see that this is indeed how my S1, S2 are. Now, once I know my B1, B2, B3, okay, and I have also got, so what is my R going to be equal to? Now, I am going to just put it down. My R is going to be equal to, if I just put it down in, you can actually do the matrix multiplication later. This is B1 transpose, then into 5 upon 6 EI 2 minus 1, 2, and then BI, which is 0, 5, 0, 5, okay, plus minus 5, 0, minus 5 plus 5, 5 upon 6i, 2 minus 1, 2, minus 5, 0, minus 5 plus 5, plus 0, 0, minus 5, 0, 5 upon 6 EI, 2 minus 1, 2, sorry, this would be 0, 0, minus 5, 0, 0 minus 5, 0. This entire thing multiplied by 10, 0, plus minus 5, 0, 5 multiplied by minus 1 plus 1 of 62.5. If you do all these computations, you will get your displacements R1 and R2. Okay. So you've got your S1 and S2, you've got your R, and that in a sense is what are these terms? This term is the contribution to the flexibility matrix of member 1. This is F2, this is F3. So if I add F1, F2, F3, that gives me the complete flexibility matrix multiplied by 10 into 0. So this gives me the structure flexibility matrix for this particular structure. Okay, and you will also notice something else, that in a structure flexibility matrix, remember the member flexibility matrix was what? 2 minus 1 minus 1 2 into L upon 6 EI. Did you notice something? It was symmetric. Okay, when you do these computations, you will see that the structure flexibility matrix is also symmetric. What does that mean? That Bij is equal to Bji. Okay, or I'm sorry, Fij is equal to Fji. Now, what is this flexibility? If you look at it, what is F11? You know, you will get in this, you will get F11, F12, F21, F22. Okay, each one you can evaluate. What do these mean? Let's look at this. What does F11 mean? F11 is the displacement at 1 due to a unit R1, capital R1. F22, displacement at 2 due to a unit load corresponding to R2. Okay, what is F21? It is the displacement at 2 due to the unit load corresponding to R1. And what is F12? The displacement at 1 due to a unit R2. Now think about this. Displacement at 1 due to a unit load at 2 and displacement at 2 due to a unit load at 1. Shouldn't they be the same? Which law is that? The Maxwell's-Betti reciprocal theorem. Okay? If you look at that, then automatically these two are equal to each other, and you will see that this is also a symmetric matrix. Okay? A symmetric matrix is one in which the transpose is equal to itself. That is what a symmetric matrix is. Okay? This additional term essentially comes from the effect of the local load. So we've considered the load effect of the structural loads and the effects of the member loads. And obviously this is going to be a superposition of the two. This in a sense is structural analysis the way it is. Okay. Now remember I said that SI is equal to BIR in this particular case. When do we need to consider some additional terms? Okay. We will see that there will be SI will not only be just BIR, there will also be an SI0. Where does this SI0 come from? So in other words, when you plug this in, you will see that ultimately R will have three terms. One term will be summation over I BI transpose FI BI into R plus summation over I of BI transpose FI S0 plus summation of I BI transpose VI0. So in other words, this in a sense is the real thing. Where does this SI0 come from? Let me take a particular problem that I am going to look at. Okay. Now don't be worried that I am not solving all the problems. I am illustrating all the equations that I am talking about. Let us take the same problem that I have. Okay, and instead of applying the load here, I still have this 10, let it be. Okay, and I have a 40 kilonewton load acting at the center. Now, note that there will be two aspects to the problem. One is this member load. Okay, see, this is, we are still finding out R1 and R2, and we are finding out the S, the member end moments. Now if you look at this particular case, there will be two aspects to this. In this particular structure, one aspect of this load is going to be the effect of the local VI. There will also be another. If you look at the member end moments, let's do the member end moments here through the traditional approach. What will be the member end moments coming out to be? The traditional approach, we take the load and find out. This is a statically determinate structure, I can solve for it. Let's solve for it. What will we get? You will get here, due to this load, you will have sigma fx gives you that this is equal to 50. Okay? Take moments about this point. Okay? You will see that this into 10 plus 5 into 40 is going to give you what? It's going to give you 200, 250, 250 divided by 5. So this is going to land up being equal to 50, and this one is going to be equal to 50. So if we find out the member end moments, let me draw the bending moment for this. How will the bending moment look? $250 here. Okay, then, and what kind of a moment is this? This is going to be a moment like this. Okay, then here this is also 250, obviously from equilibrium considerations, and you have 50 over here. So you're going to be having 50 into 5, 250, and so this is going to be equal to, let's see, this is giving rise to, over here you have right, and if you look at this particular point, what moment do you have? You will see that you will have 0 moment here. Now let's look at this. Here, what is the shear force? Here you will see that the shear force is going to be 40. Okay, so if you draw the bending moment, okay, let me just take you through this step by step. Okay, we've got the things. So this is going to see this, and on this side is going to be in this direction. This is 50. This is 50. Here this is 50. So on this side is going to be 50. And so, if you look at it, the moment over here is going to be in this direction, and it's going to be equal to 250 kilonewton-meter. Let's look at this. Here, this is 0. So from here to here, there is no moment, and then from here here what do we have? We have 40 here, 40 here, and we are going to have 50 here. Okay, so what's going to be the moment at this point? You will see that since this goes this way, this will go this way, and it's going to be equal to the fundamental mistake. Here we have actually, this is where I made the mistake. This is 30, and this is 30. Because if you take moments about this, 40 into 2.5, so that is 100, 100 plus 150 divided by 5 will give me 30. Okay, so this is going to be 30, 30, 30, 30. So over here, what do I have? I have 40 into 2.5, so that is 100 kilonewton per meter. And let's look at this one. This one is going to have 40 this way, 40 this way, 30 this way, 30 this way. Moment over here is going to be 250 over here, and so if you take moments about this point, this is going to be 30, so this is going to be 100 over here. Okay, so if you look at the bending moment diagram, it will look like this. Okay. So that is going to be the bending moment. Now the problem that you will have over here is, this is the bending moment diagram as we have it. Okay. Now I am going to show you, I'm going to end my lecture over here, but next time I'm going to be showing you how we are going to get this exactly the same bending moment diagram by using the concept of SI is equal to BI into R plus SI0, and we will see what SI0 actually stands for in general. Okay, so thank you for today. We're going to continue looking at how to look at the flexibility approach for beams and frames. Beams, we are doing simply supported, so simply supported statically determinate beam is not an interesting problem. Okay, so that's why we're looking at a statically determinate frame. Okay, and we'll continue with this particular lecture as we look at it next time.